It is a great pleasure to introduce Thomas G. Farr, who is a researcher at the Jet Propulsion Laboratory. And Tom received his Bachelor of Science and Master of Science degrees from Caltech and a Ph.D. from the University of Washington, all in geology. After a short time as an engineering geologist, he joined the Radar Sciences Group at JPL, where he's been since 1975. At the Jet Propulsion Laboratory, he has helped develop the first geologic applications of imaging radar using aircraft, satellites, and the space shuttle. And the title of his talk is InSAR Measurements of Subsidence in the Central Valley of California from 2007 to the present. Very timely talk in the light of lots of things going on in California. Please welcome Tom Farr.
Well, thanks, Dave, for the invitation. I really enjoy coming and telling people what we do. You know, it's kind of fun to apply these kind of esoteric techniques that I'll be talking about to real world problems that we've got in the Central Valley and elsewhere in the world. So I'll be talking about this wacky technique called Interferometric Synthetic Aperture Radar, but I'll call it InSAR for short since we don't have that much time. Basically, the idea is that, as most of you probably know better than I, that some of these things like groundwater that's becoming more and more important throughout the world in arid regions is providing a lot of water, but it's not easy to measure what's going on with the groundwater. We can use water wells, and we do that in places we can do that. But not only are there kind of practical problems with that, but there's even, especially in California, political problems of getting the information about water wells and the height of water in wells. So in an indirect way, we can use this InSAR technique to look at surface deformation or subsidence related to pumping of the groundwater, and I'll go into that in a bit more detail in a minute. Also, and especially important to the California Department of Water Resources, who are actually funding my work, is that this subsidence causes a lot of problems for infrastructure, roads, bridges, and especially canals and aqueducts, and I'll show you a little bit about that. But obviously the water needs to flow downhill, and if you've got a low spot in the canal, it's not going to flow as well. And so they're worried about that. And then trains, interestingly, I'll point that out if I remember, that the California High-Speed Rail is planning a route through the Central Valley. It goes right through some of these subsidence areas. And so I've spent a lot of time on the phone with those folks talking about what we can tell them about the problems there. So what I'll be showing you here is some information products that we've been trying to develop for water managers. You know, they're not satellite geeks like us at NASA, so they need something that they can understand and that the public can understand. So we're trying to produce different kinds of products that the public can get into, but also then some more quantitative products that hydrologists at these places like DWR can make use of and look for problems. And especially things like maps of hotspots, something that we can give them a heads up that, hey, there's a problem in this area, and you'll see that there's a few areas in the Central Valley that have recently started subsiding and that they wouldn't have known about that otherwise. So I'll show you some of these different kinds of products. And I'll mainly talk about the Central Valley here, but recently the DWR has asked us to basically cover the whole state and start looking at subsidence in other areas. We know there's subsidence in Antelope Valley, for example, and other places. So we'll be starting to focus on those areas as well. Focusing on the Central Valley again, it's kind of surprising. It's a place that a lot of us don't really know that much about, but it's basically the whole central part of the state here between the Sierras and the Coast Ranges. And I was kind of staggered by the amount of food that's grown there relative to the whole country. So it's a really important area in terms of food production, but especially the southern part of the Central Valley, called the San Joaquin Valley, is a quite arid region. So they basically use a lot of groundwater to grow those crops, but because the weather's so nice, they can grow a lot of crops. So it's very important, but it's very susceptible to problems with water delivery. And no surprise, when there's not much precipitation in the blue line here, back in the late 2000s here, the precipitation went down and the groundwater pumping went up. And this is just up to about 2010. We had a little bit of a wetter winter at that time. But if you then go on and look at another way of looking at the time period from 2011 to 2015, the red dots here are wells that have gone down more than 50 feet. The water in the wells have gone down more than 50 feet because of the pumping, and the orange ones aren't much better. So you can see a lot of exploitation of groundwater in these areas. Oh, and that reminds me, I'm sorry, but I'm going to be switching back and forth and mostly using American units because the DWR wants me to give them everything in inches and feet. So hopefully you can do a mental transformation to do that. But I haven't had the time to make two sets of graphs for the different measurement types. So it's a problem, and subsidence, the pumping is a problem, and subsidence is a problem. It's been a known problem for many years in the Central Valley, even well before the 60s. I'll show you this area in the western part of the southern Central Valley and the San Joaquin Valley. That's a well-known trouble spot where there's been a lot of subsidence over many years. And but basically in the 60s, the State Water Project and all these big canals and things were put into place and brought water from the northern part of the Central Valley, which isn't nearly as dry, down into the southern part, into the San Joaquin Valley, and that ameliorated a lot of that, and the water levels came back up in the wells, and the subsidence slowed down. But now we're back at it. We've had a drought for many years, and so they're pumping like crazy in these aquifers. So what happens in this? And my friend Sarushian always reminds me that I have to emphasize that this is a type of aquifer system that's susceptible to this. Not every aquifer can do this, but in the Central Valley we have kind of an alluvial system where we have mixtures of sand and gravel and finer grained layers called aquitards, which are made up of clay and silt. And so it turns out that the action is actually happening in these fine grained layers. When you pump the water out of this system, the water gradually drains out of those fine-grained layers. They compact, as you can see on the right-hand side, and that's reflected at the surface by this subsidence. So that's kind of a specific kind of aquifer system. It's not uncommon around the world, but things like fractured rock aquifers or karst aquifers won't necessarily have this happen to them. Now you have a couple of kinds here. You have a reversible or elastic deformation that we have where as the water comes and goes, the ground surface goes up and down. It's kind of a seasonal effect that we see in a lot of different places, and I'll show you that for the LA Basin. But if you keep pumping and keep pumping, then the land surface will just go down, and there's a point where it becomes what we call inelastic or irreversible, and you lose a certain amount of ability to store water again. If the water comes back, it won't be stored. And that's sort of a cartoon over here. It's called depth to water in this graph, but you can also call it subsidence as well. And you see this fine-tooth pattern here would be the seasonal effect. But if you're pumping more and more every year, then you have this long-term effect of dropping the water level and the ground surface. And here's a few examples of what's been going on in the Central Valley. This is on the left here is a famous picture of Joe Poland, an early student of subsidence in the Central Valley. The top of this is just schematic, obviously. The ground surface wasn't actually at this level on this telephone pole. But in 1925, the ground surface was 9 meters higher than it was in 1977 when the picture was taken. 9 meters over 50-some years, so that's about 17 centimeters a year, about 6 inches a year if you average over that time period. And that's over in that west side of this San Joaquin Valley that I mentioned to you. Now, more recently, you have things going on here. You can see somebody's had to block up these pilings holding this pipeline. You want the fluids to flow, and you've got to keep it high enough so that it'll flow. Here's a wellhead, cement wellhead, and the well here, so the ground's dropped around the well and exposed that. My colleague Michelle Sneed at USGS gave me this picture. This is another well casing here, and about 3 years before this picture was taken, the farmer painted the well casing because it was sticking out of the ground, and he would hit it with his tractor if he didn't see it. Now the ground is sunk about, I think that's 2 or 3 feet in that 3 years there, so it's exposing more of the pipe. So I guess you can see it better, so it's not as big a problem. Okay, so this technique called InSAR. I'm not going to spend a lot of time on this because I could spend all day talking about it. There's so many ifs, ands, or buts about it. But essentially what we're doing is using a satellite, or we can also use an aircraft, to take multiple pictures, multiple images of a particular area on the ground. And if something has changed, if the ground has moved, we can actually measure that movement as a function of the waves that are coming back from the surface. Because the radar is a coherent sensor, we can measure the actual position of the waves, where it is in its up and down cycles, when it comes back to the radar. So we take a picture before, and we come back a month later, a week later, whatever, and take another image, and the ground has moved a little bit, and then we can compare those two images, and we make an interferogram, which is like the interference fringes, the colors on a oil patch on the water. And we make something like this, where the fringes here indicate how much the ground has deformed as a function of the wavelength. And in this case, the wavelength was about 5 centimeters. We can see fractions of that wavelength, so we can measure down to the few millimeter type accuracies, types of motions. So, you know, as a geologist, this kind of blew my mind when these guys came up with that. This is an image of the Landers earthquake, actually, and these fringes represent the deformation of the earth. The fault runs right through here, and each fringe here, the engineers like to make these colorful fringe patterns, but each color cycle here represents a half a wavelength, again 5 centimeters, so a full fringe here is about 2.5 centimeters, about an inch. So you can count in here towards the fault, and you can measure that there was about 7 meters of offset on that fault. So it's just amazing. So obviously there's lots of applications of that we won't go into. But then a few caveats and a few of the details here about this. For one thing, you can see here, as shown here, the radar is sensing to the side. So it's actually measuring a line of sight change of the surface along this slanted path here. And most of the radars work from about 30 to about 50 degrees from vertical. So you get that kind of projection, you know, at that angle. What I'm doing is looking at subsidence as the most important change in the surface. So what I do in my processing, post-processing, is I project that line of sight motion to vertical. I assume that all the change that I see is vertical. And that's reasonable in areas that are more or less uniform, but I can't do that, say, across the San Andreas Fault. One side or the other is moving sideways a lot, and so that would cause problems for me. So I restrict myself to, I keep an eye on where the faults are. Another couple of caveats about this technique is that we're relying on what we call phase coherence for these areas. In other words, at the scale of the wavelength, we can't tolerate the ground to change too much within a pixel. And typically pixels are 10 to 100 meters kind of in scale. So what that means is that if we have vegetation and the wind's blowing and the leaves are blowing around, that's more than an inch or so. And so that can actually spoil our phase coherence, and we can't get a measurement in those areas. And you'll see examples of that. The other thing that bothers me in the Central Valley is those pesky farmers who go out and plow their fields. So within a pixel, then, there's going to be all this random change at the wavelength scale, and so I can't get any information there. But luckily, there's enough fields that aren't plowed each time so that I can make my measurements. Another thing, and you've probably heard, radars can see through clouds and are unaffected by the atmosphere. Well, the phase velocity here from the satellite to the ground is affected by water vapor in the atmosphere. And the people that work with GPS know this very well. They work in the same wavelengths. And so that can actually cause a phase delay that looks exactly like the ground changed. And so that's kind of a problem that we really don't know how to deal with very well. The best way we can do is collect many, many pairs, and as I'll describe, and kind of average out that effect of the atmosphere changing from time to time. We try to use weather models, but they're not quite good enough to do that. So those are kind of two of the main things. Make sure I covered everything here. Yeah. Now the next thing is this is a single interferogram, 2 images, one before the earthquake, one after the earthquake. What we really want to do is see long-term changes in a surface over years. And so what we do, and these satellites are very good at that, they return to the area every month, every couple of weeks. The data I'm working with now from the European Space Agency returns every 6 days. So we're getting an image every 6 days that we can make pairs. So we end up with hundreds of pairs. And we have another special software package that actually inverts all those possible pairs into a consistent time series, is what we call it. And I'll be showing you examples of those time series, but they're essentially like a movie of the surface as it goes up and down and does whatever it does. So we can actually see details of what's going on, and I'll show you some examples of that. So I think that's about everything there, but it's complicated. If you have more questions, that we can talk about it afterwards. Now, luckily, California is a popular place for radars to look at the surface, especially because we have lots of earthquakes, and so they want us to test their techniques out. Because none of these radars here, these radar systems here, are U.S. radar systems, except the last one here, which is yet to fly in 2020 or 2021. The Europeans, the Japanese, the Canadians, the Germans, Italians, and the European Space Agency. So we've been exploiting these data sets, and luckily they've been acquiring data over California for all this long time period. Generally, though, these later ones are better suited for the InSAR technique. And you'll see some of the different parameters here. That's not too important, just to note that we have a lot of different data sets to exploit. Okay, this is one of my kind of sales images that I use. It's relatively old. It only ends in 2002. But we've shown this to people, and it really opens their eyes on how this technique can work. I'll start the movie in a moment, but the geologists will recognize here a discontinuity along here as the movie goes along, and that's the Newport-Inglewood Fault that runs through here. It forms a groundwater barrier, and so we see changes, differences in what's going on the surface with that. And then notice the color scale here going from -5 centimeters to +5 centimeters, so we can, that's the kind of accuracy, again, that we're going to see. And what you'll see is, if you watch the timeline, you'll see a seasonal effect here. That's the elastic component there of the ground going up and down as water's pumped out. Here's that discontinuity I was mentioning. As water's pumped out in the summertime, and it recharges the aquifers in the wintertime. There it is. Also notice over here in Pomona, an area that just went down and didn't really come back up. And actually, we discovered that and pointed that out to the folks, and they were over pumping the groundwater, and they actually had to start dealing with that over the last few years. But this is just amazing to be able to come up with this kind of acuity in what's going on the surface. And what you can do then, what I did is I went to a particular well here in Long Beach, and 2 different frames for that movie, and I plotted the deformation in red here for that point, and then on the water height in that well over here in the blue. And you can see that they track very well. Again, they're pumping in the summertime, so it's going down, and it's recharging, and so it's reflected in what's going on the surface. So that's kind of a more or less one-to-one correspondence there. So we go to the Central Valley now, and this is a period from 2007 to 2011. And we'll look here. This is the southern part, the San Joaquin Valley. Notice the color bar that only goes one way. That tells you a lot right there. So we're going from 2007. It's in the drought, early stages of the drought. And you can see this area right here. A known area of problems is around Corcoran, north of Bakersfield. And you can see the surface is just dropping and dropping and dropping. If you're really sharp-eyed in the winter of 2010, 2011, it kind of stops a little bit and maybe even reverses slightly. It was a wet winter, and so they either shut the pumps off or had some recharge in that. But basically, it just keeps going in a very linear fashion. So that's what really gets people worried. And again, 70 centimeters here in about, what is that, 5 years. So it's, you know, it's really moving down. What is that rate? Do I have it? No. So we can make more kind of prosaic maps here to get a little more of the quantitative information across. And so over here on the left here, this area is what we were just looking at in terms of total subsidence here. And again, this is in inches now over that time period. And then up here, there's another area here that's relatively new. It started in the early 2000s. It's an area that a lot of tree crops were planted up in there. And so they need water year-round, and they were starting to draw the water table down significantly. Now, as I mentioned, we can also get more details. And so in the center part of these two subsidence areas, I plotted over time the amount of subsidence. And it's, I think it goes down to 40 inches here, again, in inches. So you can see then over this time period, it went down almost 40 inches in the center of this one. The center of this one was a little bit less, but it basically went down too. And you can see then each one of these dots represents an acquisition from the Japanese radar. So the DWR asked me to kind of follow up with this and see what other newer data we could get. And so we were able to get data from the Canadian satellites for the second half of 2014. And so you can see the same features here. Actually, I'll point out this little feature here. It wasn't here. It's showing up here, and you'll see that in a minute, has grown. If you look at the rates here, again, the same two areas, the rates pretty much doubled in this time period between 2011 and 2014. And you might say, well, this is, you know, the summertime or only half a year, so we need to corroborate that, and I'll show you that, indeed, it's kept up that rate. Now, you can do other things with these data sets. I kind of like to think of it as they're sort of like four-dimensional data sets. You've got the map here, you've got the third dimension of the subsidence, and then you've got time. You've got steps through time. And so you can do things like here, what I did is along the California Aqueduct here, I plotted different times of what's going on that area. And so the first date, and I neglected to mention that all of these measurements are always relative to the first date that we have an image, and then everything's calculated from that. So that first date, we have 0 deformation, and then each of the subsequent dates, you can see it goes down more and more. But it develops some interesting structures here, a very narrow structure here that then widens out at the later date in this location, and then here's another location on the aqueduct where we see significant, it's a significant local low spot, so it's an area that they're going to have to deal with. They actually build up the sides of the aqueduct to allow the water to pass through there at continuing high rates. This is the other area, and again, another deep subsidence area. You see this line running through here, that's called the East Side Bypass. That's a flood control canal. And right now, there's been a lot of email traffic with me and some of the people at DWR concerned about that, because now we're going to have a lot of water coming off the Sierras pretty soon, and they're concerned that this is not going to do its function. Right in the middle there, it's got a real low spot. So now what we have, I mentioned that the European Space Agency had a satellite here called the Sentinel-1. There's actually 2 of them, 1A and 1B, and that was in that chart there. I should have pointed it out, but that was just launched in late 2014. And amazingly, the European Space Agency is giving away the data for free, like NASA does. So we've been really fortunate in being able to get these large amounts of data now for all of California. So now I'm able to start processing these large amounts of data. And they're very wide swaths, they're peculiar formats, so it took us a while to figure out how to process it. But I'll show you some details from this path here that's underneath everything that runs right up the middle of California. And then I'll show you some processing we've done for this one through the northern part of the state as well. But basically, we're using all of these here to start looking at the different areas. And again, with the 2 satellites, they can actually cover the area every 6 days. So we're at the point of getting drowned in data, which I'll try to address at the end. Well, here's the same area, the same areas here. You can see they're almost merging now. Here's the northern one and the southern one. And just to address the rates to start with, in the red here is the radar sat data, that data from the late 2014, and here's the new Sentinel data, and you can see the rates are pretty much the same. The rates continued at that very high rate right up into 2016. This map actually represents 2015 to 2016, but again, you can see the areas have increased and deepened, and then you see this one that I pointed out here, this new one is actually really picked up and is a very high rate right in between them. You also see how it's really impinging on the California Aqueduct now, and so they're really getting some trouble here, and I'll talk about that in a minute. Yeah, this is the kind of product then that I'm producing for the Department of Water Resources. Now here's another video here, the same area we saw earlier, but now this is with the Sentinel data up until the end of December in 2016. And I'll show you plots then from these two places. These are the centers of those two subsidence bowls. And again, the color bar only really goes one way. And then we've got the dates down here. And so you can see then as we march along here that they're just dropping and dropping. It starts at 0. Again, that's our reference date. It goes to 30 inches here is at the bottom. And you can see the red one is this Corcoran bowl, and the green one is that El Nido bowl. And interestingly, I'll talk about this later on, is this green one actually levels off for a while in the winter of 2015-16. And it turns out there was some rain during that time. I had kind of forgotten about that. But that apparently was enough to really slow down the subsidence. The Corcoran feature, though, just keeps marching down, and then they both pick up again. But again, you can see how closely spaced the dots are now. We're really getting a lot of resolution in there. And then a suggestion of a turn up at the end here, again, from the more recent rains. So it looks like rains do affect the subsidence in some way. And here's just those two plots along with a couple of other areas. This Avenal feature here next to the aqueduct, and this new area near Tranquility, the town of Tranquility. So you can see they all had this shelf here except for the Corcoran feature. And here's a comparison now with GPS in these areas. So the Corcoran and the Lemoore stations here are these upper two ones, and you'd see they track quite well. There's some deviation here. And then a couple of other stations here do kind of depart from the GPS, which is in the red. And the best I can determine is that that's probably caused by water vapor variations again. Remember that those can cause changes in the perceived deformation. And these amounts here, you can't really read it, but these amounts are on the order of about 1 inch deviation. So, you know, we can kind of hope that that's it's still accurate enough when you've got 40 inches of subsidence in the areas that we're worried about. Now, I mentioned we can also work with aircraft, and this is an airborne InSAR that we have that NASA flies. It's pretty tricky to collect this kind of data, but we have modified the aircraft to do that. And one of the nice things about that, it's a narrower swath, but if you fly along, say, the California Aqueduct, you get higher spatial resolution that way. And plus, you can fly in any geometry and any day you want. So just to focus in on this area, Kathleen Jones at JPL has then changed the color table, but you can actually see this bullseye here right next to the aqueduct that's affecting the aqueduct. And in fact, that's actually one well right there. And we gave the DWR this information, and I think that they went and talked to somebody, but that's not our job. Now, the other area is the northern Central Valley, the Sacramento Valley, and this is another pass here, and it's just a couple of interesting things. There's an area at the town of Arbuckle here, which has subsided quite a bit. The full range here is about 12 inches, so it's gone down about 12 inches, although leveled off in that same winter. I don't understand why that one little area is having such a problem. And then up here in Sierra Valley, it's a little area north of Lake Tahoe, we found that that's subsiding a bit. And I actually just got an email today from them that they'd like to see more information about that, so that they'd like to find out what's going on with their area. And again, comparison with the GPS, those track a bit better. So one of the things that that I've been kind of puzzling over just recently, this is stuff I've just done in the last week, is why did that rainfall cause a almost instantaneous stop of the subsidence? The traditional ideas are that recharge of these aquifers can take years or decades to get the water down that deep into these aquifers. And so, but we're seeing in this case, here's the deformation in red, and then this is that's the water surface elevation in the well. And the water surface in the well comes up, and only a couple of months later, the surface is reacting. And similarly here with the rain and the rainfall and the water surface in the well. So they're reacting very quickly, and I think my current hypothesis is that what happens is as soon as it starts raining, the farmers turn off their pumps, and so then the subsidence basically halts right after that. And as soon as they turn the pumps on again, it may go back up. So I'm actually in contact with some of the farmers and trying to get some of the data that they have on when they had their pumps on and how much were they pumping for different time periods. So we'll see if we can correlate that. But that's an interesting kind of question there. The other thing, obviously, is what is the subsurface geology like? I should have pointed out in some of those areas, like the Corcoran area that's dropping so fast, it might be just an unfortunate coincidence that they have a lot of these clay layers underneath them. And when they pump the water, they just get a lot more subsidence, whereas other areas may be pumping almost as much, but if they don't have the clay layers, then they won't subside as much. So there's kind of a two parts to that problem, pumping and the geology. So I wanted to talk a little bit about kind of what's going on into the future here. As I mentioned, we're starting to get these huge data sets every 6 days. If we cover the whole state every 6 days, that's many terabytes of data. Right now I'm working with tens of terabytes of data just on my server, and it takes, each one of those points on those graphs takes several hours to produce on my server. So I've got a couple of jobs running right now that I'm hoping will finish over the weekend. But that's just, you know, it's going to drown us very soon. And we have this NASA satellite coming in a couple of years that will produce even more data and better data than this. So we're starting, we've started a project to try to get used to keeping up with that kind of a data stream. And so we've got some of these big data cloud processing folks, you know, helping us out. And what we've put together is what we call the Advanced Rapid Imaging and Analysis project, the ARIA project. And this is just an example of Kilauea, another place where we want to try to keep up and keep monitoring the data. And this is with the Sentinel data. They're acquiring it from the different locations and trying to keep up with the interferograms. And so this, I'm actually stressing the system even more with my demands because this is just a small part of an image, and I'm trying to cover the whole state. So they're actually kind of interested, the engineers are interested in my problems, so that's kind of nice. But trying to keep up with this kind of processing to these interferograms is tough, and then trying to convert those interferograms to the time series, the next step is yet another big problem to invert all that data. Once you have several hundred interferograms, trying to invert that is starting to become almost intractable. So we're trying to figure out ways to kind of stage that in pieces maybe. So these are just the kinds of software that we use to do this, and we're trying to make use of the cloud just to try to save data transfer and processing, trying to bring those all together to make it more efficient. And this is just an example here of one of these time series for the Kilauea area that they're able to do. So this is the kind of thing that they can do potentially on demand for users. So you can go and find your area and have it processed for you and have the time series delivered to you. So somebody like me, a geologist, you know, that's what I want. I don't want to know about unwrapping, phase unwrapping, and all these kinds of problems that the engineers have mainly solved. Once we have this kind of stuff, then we're starting to think even bigger, and we're starting to work with Jay Famiglietti, who many of you know, I think, He's the chief scientist of the Western States Water Mission at JPL. And what we're trying to do there is factor not only this subsidence information in, but information from other satellites like the GRACE gravity mission, the Airborne Snow Observatory. We have other satellites, a soil moisture mapping mission. In the next few years, we'll have a surface water mission that'll measure the height of water in rivers and lakes. And so we can start factoring these observations, the hard data, into the models that so far have used models as inputs to the models. Now we can start giving them actually hard data to start trying to model large areas like the whole western states in terms of the hydrology and what's going on. And also try to derive the uncertainties that go along with those measurements. So it's kind of a grand vision, but it's the kind of thing that I think we're now kind of at the cusp of being able to do with all these measurements that we're able to get through the NASA and international communities' satellites. And just as kind of one example here, this is something that we're working up that we'll be presenting to the management at JPL pretty soon. We call it Water Trek, but it's a way of visualizing a lot of these kinds of data sets. So each one of these little bars here is a data set. There's all the water wells in the area, the water height in the water wells. There's shape files showing where the aquifers are in map view. There's my subsidence time series are in there, and snow measurements and water flow, stream flow in all the rivers in these areas. So all of those are available to visualize, and then you can start doing things like cross correlations of these different types of data. One thing that I'm very interested in is trying to cross-correlate the height of the water in the wells with the subsidence, so we can start looking at which wells are behaving elastically and which are not. And you can start seeing that when you start doing the cross-correlations. So that's basically all I have. That's well, actually I had a couple more that I can show that are kind of interesting. This is an example of some of the GRACE here. You can see here the little bug crawling along here and seeing the total water storage here that they've measured. And you can see then when the drought kicks in, the mass deficit here measured by the GRACE satellites really shows up. So that's another measurement of what's going on below the surface in terms of mass. And what I'm seeing is essentially changes in the pressure in the confined aquifers. So we're trying to figure out ways of modeling that, of bringing those two different data types, different measurements together to understand the aquifer systems better. And I'll stop there. That's kind of a nice one. So thank you very much, and I hope it was entertaining.